Section 2.3, the limit laws. In this section, we're going to learn quite a few laws that allow us to evaluate limits. We're going to specifically focus in on polynomials, rational functions, some trig functions, and we're going to deal with some unfortunate indeterminate forms, but algebra will get us out of trouble here. Let's start with two basic limit results. We have one limit result for the simple case where we're looking at a function that's equal to x. If I want to know the limit for this function, x, where x is approaching some number a, well, this notation at the bottom, x is approaching a, it's basically saying we'd like to replace x with the value a. If our function is simply x, then we replace it with a. So the limit for the function x, when x is approaching a, is just a. Next, we look at the case where we're looking at the limit of a constant. So if we're looking at the limit of some constant c, and we let x approach a number like a, well, constant is constantly constant. It doesn't change. It doesn't matter if x is approaching a. This constant does not depend on x. So the result is the same constant. It's constantly constant. So we're going to practice this. Some of these seem too easy that they can become hard. So let's make sure that we understand how to use these basic limit results. The first one, I have a function x. I'm allowing x to go to 2. So I'm going to take the x function here and replace it with what x is approaching, 2. Next one, the limit of the constant 5. X is approaching 2, but 5 is 5 all day long. X going to 2 does not change that. Next one, I'm looking at the limit of the function x. X is approaching -1, so that tells me to replace the x with -1. Now I'm looking at the limit of a fraction. Although we don't typically like fractions in this area, a fraction's just a number. It's a constant. So 2/3 is 2/3 today, tomorrow, yesterday, whenever. X approaching 2 is not going to change what 2/3 is. So that limit is equal to 2/3. Next, I'm looking again at the limit of the function x. This time x is approaching 0, so we will replace x with 0. I have another one down here, the limit of the number -1. That's a constant. Here x is approaching 2, but -1 is just -1. It doesn't depend on x, so I'll copy the -1 over. Now let's talk about some of the other limit laws. To start off, let's take a second to agree on a couple of things. We're going to look at two separate functions, f and g, and luckily for us, we are going to be given the value of the limit as x approaches a for each one of these functions. If we wanted to evaluate the limit where x approaches a for the function f, we know the answer would be the number w. And if we wanted to evaluate the limit where x approaches a for the function g, we know the value would be n. So that's to say, if I write the letter n, it's the same thing as writing the entire limit expression that it's equal to. And if I write the letter m, that's the same thing as writing the entire limit expression that it's equal to. So we'll quickly go through these laws, and then we're going to use them. So we'll start with the sum law. The sum law says that the limit of a sum, so if I'm taking two functions like f and g, I'm adding them together, then I apply the limit. That's the limit of a sum. But I don't have to do it this way. I don't have to first add the two functions together. Instead, I could do the limit of each function separately, and then add those limits together. And that's what I'm saying on the right side with m plus n. Remember, m is the same thing as the limit as x approaches a of f. And n is the same thing as the limit as x approaches a of g. So we don't have to add the two functions together first. We could just add the limits together after we've computed the individual limits. That works for addition. It also works for subtraction. So if I have my two functions and I'm subtracting them, then I'm applying the limit. I could do it that way, or if I happen to know what the two limits are individually, which we do, then we could just do the difference between the limits. So the limit of a difference is the difference of the limits. Next, let's look at the constant law. This says that if I have a function like f of x, and I'm multiplying it by a constant k, now I know constant's spelled with a C, but we already used the letter C for the constant limit law that we saw before. This constant limit law is for a constant multiplier. This dot between the k and the f represents multiplication. So this law is telling us that if I have a function and it's being multiplied by a number and I want to take the limit of that product, well, I could just multiply the limit of f by that constant k. So I can factor constants out. And again, I'll show you how to use that in this video. Next, we have a product rule. This says that if I have a function f and I'm multiplying it to a function g, and I want the limit of that product, I could do it that way, multiply the functions first, then apply the limit. Or if I know the limit of f and I know the limit of g, which we do, we could just multiply those individual limits. It would give us the same value. Next, we have the quotient law, which tells us that if I have a quotient between two functions and I take the limit of that, I could have done the limits individually. In my numerator, I have the function f, so I put the limit of f on top. In the denominator, I have the function g, so the n goes on the bottom because n was the limit of g. Two more rules. We have the power rule, which tells us that if a function is being raised to some power, and then I'm applying the limit, I could hold off on the exponent, apply the limit to just the function, which is the m we have on the right side, and then apply the exponent after. And roots, if you remember that roots are basically rational exponents, they work the same way. So if I'm doing a root over a function, I could allow this limit symbol to sneak into that radical, apply the limit directly to the function f, which would give us the m inside of the radical, and then apply the root outside of that. So let's take a look at how these really work. I have a function, 4x plus 2, and we're going to calculate the limit of this function. So first, let's take a second and appreciate that we have two terms here, and the two terms are being added together. So we should probably think about the sum law. The sum law says that I can separate these two terms and calculate each limit individually. Now that I've separated them using the sum law, I want to look and see if there's any limits that I know how to evaluate. Basically, my two basic limit rules. The two basic limit rules we have were for the function x and a constant. Now the second limit expression we have here is really the limit of a constant. So let's go ahead and evaluate that. We're looking at the limit of the constant 2 as x approaches -3. That works out to be 2. Let's go back to our first limit in this expression, the limit of 4x. 4 is being multiplied to the function x, so we should think about the constant multiple rule. I can factor that 4 out so that it looks like 4 times the limit. And I'm still adding the 2 to that. Now I think about my basic limit laws, and I see the limit of a function x. We know that from our basic limit laws, the limit of a function x, we just replace x with the number it's approaching, so that would become -3. But that -3 is being multiplied by a 4, and then after that we're adding a 2 to it. So this turns out to be -12 plus 2, or -10. So the limit, evaluating it using each of these limit laws, came out to be -10. Let's try another one. This function is a rational expression. I have 2x squared minus 3x plus 1 divided by x cubed plus 4. And I'm trying to evaluate the limit as x approaches 2. Now, I do see a lot of different things going on. I see differences, I see sums, I see exponents or powers, and I see a quotient. So we're going to apply many of these rules, and we're going to apply them somewhat in the order of operations. Because we have a rational expression, the first thing we need to do is separate our numerator and our denominator. So we'll start with our quotient rule. That allows us to apply a limit to the numerator and the denominator separately. Now that I have my numerator and denominator separated with their own limits, I can look for other rules that can be applied. The numerator, I have a difference and a sum, so let's go ahead and separate each of those. The denominator, I also have a sum, so I'll separate those terms. Now that I have those terms separated, I'll check and see if there's anything that can be evaluated as it's written, just to make things simpler to write out. And I see two. I see the limit of a constant here. That constant is 1, so that limit would be equal to 1. And I see the limit of a constant here. That constant is 4, so that limit would be equal to 4. So let's go ahead and rewrite those limits of constants so that they're easier to see here in our algebra mess. Now I'm going to look at my terms and see if there's other rules that can be applied. I see a 2 multiplied to a function of x. I can use the constant multiple rule to factor that out. I see a 3 multiplied to this x. I can also use the constant multiple rule to factor that out. So let's go ahead and go for it. Now I've factored out the constants, and I'm looking to see if there's anything that can be evaluated. And it looks like I have one of the basic limit laws here, the limit of the function x, where x is approaching 2. So I'm going to go ahead and replace that with the value, which would be 2. The other two limits that are left on the screen have exponents, so I'm going to need to apply one more limit law before I can replace those with their values, and that's the power rule. So I'm going to take the power to the outside of the parentheses. Now that I've applied the power rule, I can see that what's inside of the parentheses in the numerator is one of our basic limit laws. We're looking at the limit of x as x approaches 2, so I know I can replace that with the number 2. But don't forget that that's being squared. And then in the denominator, I'm looking at the limit of x where x approaches 2. I can also replace that with the number 2. And now we just need to simplify this expression, now that it's all numbers and no longer limits, to find the final answer. Adding through the numerator, I get a 3. Adding through the denominator, I get a 12. That can simplify, though, to be 1/4. Using these limit laws definitely feels tedious, so if you're not excited about it, I get it. We're going to use them just for a little bit so that we understand how we're using the mathematics step by step to get the laws that we want. But quickly we will learn faster ways to evaluate these limits.